combined solution. What is a solution? Right. Okay. So now what I'm going to do is combine. So we know what our different types of reactions are. So for single, double, replacement, and even synthesis reactions, and combustion would be probably the only exception. One of the most obvious things you may encounter typically is color change, right? Okay. So for example, if I take copper, say copper sulfate, SO4, or this SO4, okay, and we put solid plus say nitric acid. We'll say aqueous, right? When it fully reacts, the most obvious thing, because nitric acid is an acid and it's clear, right? Mixed together, copper sulfate is like blue crystals, little blue crystals. If they mix together, it's gonna make a largely blue. You're gonna get a blue solution, right? It's gonna dissolve, right? Okay. And so one way to look at that is what a spectrometer does is you have it shines light into the system. So what you can do is you can create like what they call a standard, right? So you can use that to create a standard. When I say standard, in other words, we go over concentration, right? And we go over that. So what are the units for concentration of a solution? What are the units? Yeah, what are the units for concentration of a solution? That's volume. So what will be the units for concentration? Over there having I'll call the waiter over in a second. All right. So remember we calculated molarity, right? Molarity equals what? What does molarity equal? Moles of a liter? Or moles per milliliter? You'll see that, right? Both will get it correct. Typically, because of scaling, you'll see moles per milliliter, right? That would give you the number of molecules per liter, right? That would give you concentration, right? So it's typically, so I can tell you like in the problems that we gave you previous time, right? If I say I want a 1 molar solution of copper sulfate in nitric acid, right? Okay. Then that's a concentration, right? So I want this to be 1.0 molar. That's the concentration. How concentrated I am, right? So what you have to do is how many grams of copper sulfate would I have to put in that solution? Let's say I have 1 liter of nitric acid, right? How many grams of copper sulfate would I have to put in there for 1 molar solution?
Yeah, 1 liter. So that'd be.
So let's say I know I have 1 liter of nitric acid, 1 liter. How many grams of copper, the powder, it's a blue powder, how many grams of copper sulfate would I have to input into that 1 liter of nitric acid for it to get a concentration of 1 molar? How would you solve that? Exactly.
Get the who first? The weight?
Right. Now, this is probably the crux of a General Chemistry 1 course. That's what all these single, double, and synthesis reactions are doing. You want to know how many grams do I need to add to this aqueous compound, which is nitric acid, or could be water. How many grams do I need to add to get that particular concentration? That's a basic problem. So first thing you have to do, you have to go to your periodic table, right? You have to get the molecular weight. So you can find out molecular weight of copper, molecular weight of sulfur, right? And molecular weight of oxygen times 4, right? That's going to give you, what units would that be, each of these values?
You wanna know?
What are units for molecular weight? Molecular weight. Grams per mole. So each of these units would be what? Grams per mole, right? That's your molecular weight. Those are your units. Okay. Then what would you do? Right, add them all together, right? You can get some total in grams per mole, right?
No.
Now what do you do?
Take that number we just put in and plug it
I
in.
wasn't in.
Multiply that by, that gram per mole now become molarity.
Right, so you want 1 molar, 1 molarity, right? What are units for molarity? Right, or moles per milliliter. Look that up to make sure that scale is right. But in general, yeah. So you say 1.0 molarity is equal to, what is that, grams per mole. Whatever grams you're trying to find, we'll say X here, right? X number of grams over whatever this value down here is, right? Right? Then when you solve for it, right, what's my answer going to be? It's going to be X number of grams of what? Copper, sulfate, that's what I'm trying to find, right? Equal to what? 1.0. What are my units for moles per milliliter? Moles. We'll say moles per liter. Okay, we'll look that up. Double check that. Times whatever that total was over grams per mole, right? That should be correct. That mess up? Yeah, I messed it up. Sorry.
The top should be lower, right? The top should be lower, because we would cross out the moles to get the grams.
Right.
So you have grams on the top and
So
the bottom.
that cancels, right? And so, moles per liter, right? So this will give you the right number of grams. When it's all said and done, you get the right number of grams. Something like that. Okay. All right. So that's how you, in general, how you get the concentration. So sometimes they'll give you the grams. Sometimes they'll ask you, given a certain amount of grams, calculate the concentration, right? So we've done that, right? So you can go back and look at that. But you'd approach it something like that, right? Erase it. Right. right? Cause see this moles per liter right here?
Instead of putting that, you would put the F you get from all three of those up together.
That's what that is. That's what we did.
You wouldn't put that 1.0 moles down there instead of that right there.
That's what that is right there.
Switch them to around. You
Right
wanna do
there.
that?
That's what we did. We solved for grams, right? I erase it.
No.
That's not the main point. That's not the main point of what I'm saying. I'm making sure that you have some concept of what concentration is. That's the point.
Okay.
All right, okay. So that's how, in general, how you go about. So first thing, if you're not given the, if you're given the concentration up front, you're trying to find it and you know the number of grams, that's how you go about doing it. Go to your periodic table, add them all up, do your dimensional analysis. That's going to tell you, oh, I need to add, say, 1 gram or 2 grams or 3 grams, right? Of copper sulfate, which is the blue powder, blue crystals, blue powder. Okay? All right. So now you got that under your belt. Okay. So the thing is, we're going to go over here because I want to overlap with your laboratories, or or next time when you're doing something current. All right. So essentially, let's say you understand that, right? So if I get a blue color, right? If I add, say, a 0.5 gram, is going to be a darker blue or lighter blue? Right. If I add 10 grams, it's going to be a lighter blue or darker blue? Right. Okay. So that's the point. So color change gives you a very, very quick. That physical property gives you a quick indication of how much it's reacting. Okay. And so from that, you can create what you call a standard. Create a standard. So you have something called Beers something long. Beers-Lambert. Beers-Lambert law. Okay. Beers-Lambert law. Okay. And basically what it is, you have equipment there, and basically you have like a little machine, and it shines light into your system. Okay. Our system's going to be, say, like a little tube, or like a capillary tube, or a flask, right? So what you can do, right? Typically in your laboratory, you'll see a table. They'll give you a table, right? So they give you a table. They'll say, oh, okay, we want to create a standard, and we're looking at. You could be looking at copper. You could be looking at potassium permanganate, and these things. So these different chemicals have different physical properties. See, potassium permanganate would be a purple color, right? Which copper sulfate would be a blue color. Now you want to look at those different gradients of blues or purples or whatever you're looking at. Okay, iodine would be like a reddish, dark reddish color. Right? Get these different gradients of color. So you could be given a table. That table you'd be given a trial, like between 1, 2, 3, 4, 5, etc. Right? And this is important when you're testing, forensics, investigations, if you're surveying for mining or oil, many different things, right? You're going to test those different large or small scale systems, whether it's biological or geological systems. You can test to see if what you're looking there, if there's color change or not. And then on that, how much color change, right? The more color change, the more concentrated whatever you're looking for is, right? Okay, so you'd be given a trial of 1 through 5, for example. Okay, and all that trial is just different concentrations of that particular substance, right? So basically, it might be I don't know. You might put down, say, like 1, 2, we'll say 0, 2, 4, 6, 8 grams, right? Or they may have explicitly written different concentrations. Could be 1 molarity, 2 molarity, 3 molarity, different concentrations, right? You can do it that way too. Okay. So this would be your different mass. This would be your trial, okay? So what the Beer-Lambert law does is what you do is you line up these different trials. So you might have a vial, right? You might have a vial like this. And it might be clear. Nothing in there, just pure water. Because when you shine light through it, most of the light is going to transfer, right? Or transmit, rather. Transmit. Then you're going to have a second trial, right? You're going to put a little bit of your substance in, right? So that's going to be a very weak concentration, right? Then you have a third trial. It's going to be a little more concentrated. Fourth trial. So as you do your trials, the more concentrated the substance becomes, right? And then your last trial, 5, right? Really dark, right? So why are we doing that? Okay? We're doing that because you're creating what they call a standard. All right? Because those are actual, so the point is, when you really start feeling like you're doing chemistry, when you're actually able to, and it's good for when you start to do transformative research, we can start taking these things and convert them over to data points. Right? Convert these things over to data points. Okay, so let's go, we're gonna go a little more theoretical now, right? Okay, so let's look at light again. So remember at the beginning of the course, did we define light? Did we talk speed of light? So remember we said light would be C, which is equal to V, which is equal to lambda F, right? Lambda F, which is what? Wavelength times your frequency, right? Okay. So, and remember, the longer the wavelength, the more, what color? Yes. Right? And the shorter the wavelength, the more blue. That's a fundamental way of investigating different phenomena. Okay? Fundamental way. Whether you're doing earthly scale or whether you're doing the universal scale, right? Because when you look at how far the distance between the stars and the planets and stuff, that's how you can tell using light. It's called red shift, blue shift. So it's real far away, that's probably which shift? Blue shift. Close up be red shift, right? Similar kind of thing. This utilizes similar kind of thing, but we can break it down a little more than that, right? Okay, so let's look at, so remember, you can get 5 data points. Okay? See? 1, 2, 3, 4, 5. That's corresponding to 5 data points. All right, so your instrument, which is spectrophotometer, right? What happens is that you have light shining into the actual system, okay? That's going to correspond to I sub 0. That's your initial light. So initial intensity. I'll say light intensity. Right? Okay. And then, then it goes a certain distance, right? It goes a certain distance. Some of the light's going to scatter. Some of it's going to reflect back. And some of it's going to transmit, right? The clearer the substance, the more what? It transmits, right? Okay. So you've got I sub 0 is, so this would be like This would be like comparing like Jay-Z's tinted windows. You might have a lighter tinted window because he's going straight, right? He's going to clean life, right? So his windows may not be that tinted window, right? I mean clear, it'd be normal. No, that'd be me. I got clear tinted. I have no tint on my windows. This is me right here, right? So all the light goes through, right? So light comes through, it goes through the window. There's not any tint, if any, right? So you're gonna have a different intensity come out. So you're still gonna lose a little bit. There may be a little glare. That's what the glaring is, right? In the morning when you're driving, it may glare off. That's some of that light reflecting off, right? That'd be I1. So the ratio between I0 and I1, that's how much has been transmitted. We call that T1. So we say I sub 0 divided by I sub 1. This is final. So I1 is final light intensity. Okay. That equals my first transmission. We'll call it T1. So that's transmitted light. Okay. So then we're going to take a second case. This is case 1. We'll do this by cases, all right? Case number 1. Now, case number 2 would be any of my darker samples, right? Any of my darker samples. That's case number 2. Let's look at what happened. What you got like you up in church? You're like, oh, well, he's not trying to dab. Yeah.
Oh my God.
Those kinesthetic learners are something else. You know what I'm saying? They learn through feeling and movement and stuff. You're like, no. Sit here. Sit right here. Oh, it's like some kind of like a possessed or something. Just sit here. I'm a 70s baby, so I couldn't get away with that. And my dad was a cop too, right? So you walk in and be like, look here, son, you sit right here and don't you move. No, you don't move. And so like 8 hours later, I pass out. You know what I'm saying? I wake up time, go to bed. Don't work like that anymore. You know what I'm saying? Yeah, anyway, so be careful with that strong black man stuff. Man, all this cracked up to be. You know, just to be like, oh, I ain't had no father. Good for you. You were lucky, man. You just don't know, man. That's the other side I don't even talk about. I don't talk about that side. You know what I'm saying? Oh, he gone? Oh, man, you were lucky. Woo, you get out. Woo, well, you just don't realize. Boy, you missed a real huge bullet there, boy. Anything else funny? You're right. I had to do it, you know. Huh? Yeah. It's right there, right?
It was at the borderline.
Yeah, it's right there.
Then you just dropped it.
Oh, yeah. You had to let it go. Gotta let some things go. Anyway, because it's getting real theoretical here, right? So I had to break it up a little bit. Anyway, so case number 2, we have a darker sample, right? So our medium, so our system's the same distance, okay? All right. And it's a darker solution, okay? So again, you're going to have I sub 0, same intensity light initially shining through. It could be a reddish color or a bluish color, but you're going to tune it to where you're going to get, you know, the right frame of reference so you can get the values you're looking for. Okay. So light's going to be incident here. Again, that's initial intensity of light. same value there, but I'm gonna have a different transmission here, right? In other words, this solution is gonna absorb more light than the first one, right? Because it's what? Darker, right? So this is gonna be I2. This is I2, right? Okay. All right, so then you have I sub 0 over I sub 2 equal to what? T2, right? So which one's going to be larger, T1 or T2? Which is going to be larger, T1 or T2? You sure about that?
T1 is going to be larger.
Yeah, T1 is going to be larger,
It's just going to transfer.
right? So in other words, when you compare, we'll say this is step 1, this is step 2, right? So T1 is going to be greater than T2, right? More light's going to transmit in T1 than T2, see?
It's clear when it's clear.
Right. So those are my windows, and T2 is Jay-Z's tenant windows, right? He can afford to tint on his windows. Right? Now we got a third case. We got a case 3. Okay? Case number 3. Let's say we got Rick Ross, right? Rick Ross is going to have the darkest windows, but since he's big, did he lose some weight recently?
Yes.
He'll be big, don't worry. So we're going to have a larger container, right? With a darker substance, okay? So case 3, we're going to say is larger container, okay? And the darkest, right? Because he's hiding stuff, see? I mean, he's named after a famous drug dealer, right?
Yep.
Yeah, see? So we're gonna make his container like this. So you can't see through. All right? And again, we're gonna have I sub 1 of I sub 0 incident here, okay? And it's gonna be I sub what? 3, right? I sub 3. I sub 3. And again, you can get the transmission value by taking the ratio, right? I sub 0 over I sub 3, right? Equal to T sub 3, right? And T sub 3 is going to be greater than, less than, or equal to T1 and T2. Less than, right? So here, see, T1 is greater than T2, and T2 will be greater than T3 for 2 reasons, right? Actually, the path length is larger, isn't it? We can call this path length that the light travels, right? We're going to call that B. Okay. See, this is B. So we notice that the larger path length, the less light transmits because it has a further distance to travel, right? Does that make sense? Mm-hmm. Okay. So this would be your order here. Okay. Now, let's not forget, we have 5 data points, right? So this would be 1, well, we use Roman numerals. 1, 2, 3, 4, and 5, right? 5 data points. So what happens is that, remember, what's the equation for a line? Right. So remember, our equation for a line is going to be. So now we're going to get to the actual law here, right? Equation for a line is equation for line is y equals mx plus b. Okay. So what you find is that when you convert your concentrations over into data points, you get a straight line. Right? Because the so what you tend to do is you'll get something like, you might get something like this, you know, depending on the substance, you might get something like that, right? So what you do is you say, and the machine does this for you. But you have a certain transmittance, but another way to look at transmittance is how much the solution is absorbing, how much light is absorbing, right? So therefore, we can look at it from that perspective. So now that you got your transmittance values using this ratio, the machine does this for you. I'm showing you what the machine's doing in the background, right? So you've got A equals absorbance. How much light is absorbed? Absorbance. And to straighten these, sometimes you get these curvy lines when you're taking the data. You take the negative log, right? So A equals negative log base 10 of the percentage of the transmittance, right? Like that. Okay. And sometimes there's error in there, like, the glass might be dirty or something like that, or whatever. That would be your y-intercept, but typically we're going to assume it's 0. We're going to assume we're perfect scientists, right? So we're going to let that go to 0. Okay. So you've got several variables here, right? You got transmittance, that tells you percentage of light transmitted. You take the negative log base 10 of that. That's going to give you absorbance, okay? And in general, you can take, so let me show you this first. So you take your data, okay? You can end up with a plot, okay? And on the y-axis, right? The y is going to be your absorbance, right? Isn't it? So absorbance is going to be A on your y-axis, okay? Which is absorbance. Okay. What's going to be my x-axis? Because as light, the more light is absorbed, that means what? The higher my concentration. So my x-axis is going to be my concentration of my solutions. Okay. So x-axis is going to be concentration. Okay. And what are units for concentration? Grams per. No, sorry, moles per milliliter, right? Right. Concentration would be
You sure it's not liter?
moles per milliliter.